Okay, so here we are. This is part 2 of this series of videos for designing the digital clock. In this video, we will be making the driver, we will be designing the driver, and then we will be putting it all together in the final assembly, and then we will make sure that the clock is working properly. So without further ado, let's get right into it. Okay, so now we move on to the driver. So we're going to be converting the bits into something that this 7-segment display can read. So here on the left is the 7-segment display on the simulation software, and on the right is the 7-segment display in reality. So in reality, these pins, this component will come with a data sheet, and then it'll tell you which pins are A, B, C, D. It usually tells you which pins are what. But in the simulation software, it's more straightforward. And then another thing to note is that this is common anode. I actually spoke about this in more detail in my previous video where I made the hexadecimal driver. So you can go ahead and look at that video. But to be quick here, and I don't want to spend too much time on this, we see that we are effectively counting from 0 to 9. And then if we look at our table here, it goes all the way to 9, but then beyond that, it's x's. See? All of these values don't cares. So it doesn't matter what um these values are. And then these letters that we have here, well, these are, irrelevant because we don't even need them. But I guess I can change it to decimal. So if we look quickly here at the number 0, if you remember from the hexadecimal video that I posted, we're looking at this line here. And we see that this 0 doesn't have a red line in the middle. So then we go to our graph here and we see that G is what we need. So then we will place a 1 on G right here. And then you'll notice that the rest, it's all 0. So this is the process we do with the rest of the, with the rest of these letters here. And then you'll end up with a table that looks like this here. This is the important part of the table. So what we can do now is we can translate this into Carnot maps. So if we're going to do a couple examples, maybe 2 or 3. So if we look at G here, so if we're going to focus our attention now on this column here. So we see that we have a 1 here, and it corresponds to 0, 0, 0, 0. So if you look here, 0, 0, and then there's the 1. We move on. This corresponds to 0, 0, 0, 1. So this is once again 0, 0, and this time is 0, 1. So that's here. We have another 1 all the way down here, and this is the last one that we have. And then this corresponds to, right here, 0, 1, 1, 1. So then we look at 0, 1 here, and we look at the 1, 1 here. So that gives us this one here. And then what we do is we make the circles. Since this isn't we're not dealing with flip-flops here, we're dealing strictly with logic gates. We make circles right away, and then we make our expression here right away. So then the circles is this one, and this one. So let's go ahead and look at this circle here. We see that the W changing from 0 to 1, but then the X is constant, both sides. And then we see that the Y and the Z is constant as well. So then we called it XYZ here. if we look at the other circle here that we made, we see that the W and the X are constantly 0. The Z here is actually changing, so we don't look at that. And then we see that the Y's here are constantly 0 as well. So this is W not, Y not. So that works nicely. Clean this up. Take a look at an interesting one. You can pick any of these cardinal maps to look at for purposes of like looking at an example at least. Let's look at this one and then we can move on. Because this one you can take advantage of the don't cares actually here. So if you look at this one here, zoom in a bit, we see that we have, now we're looking at E. So we're shift our focus to this column here. So then we see we have a 1 here. So that corresponds to, well, that's this one here. We have another one right here. Corresponds to this one. And then, you continue this process. So there's 1, 2, 4, 6 ones that we see here. So then here we also see that we have 6 ones here. So that's in total 6 ones that we have. So the good thing about clean this up. So you see here, the good thing about the don't cares is that we can circle them and it doesn't affect our design at all. In fact, it improves our design because we can greatly simplify the amount of logic gates that we need to use. So the first circle we can make here is this one. And then the second circle is obviously this one. So let's look at the expression for the first circle. We see that the W's and the X's on all of these are constantly changing, so we don't look at that. And we see that Z is 1 here, right here, in both cases. So then that is essentially what we use to find for the expression for this circle. We use E. And then we have here this other expression here. We see that the W here changes, but then we see that the X stay the same. And then we also see that Y stays the same, stays at 0. So then we say, and then we also see that X is 1 here on both cases. So then we simply call it X, Y not. Now let's just clean this up. So this is essentially how we do these cardinal maps. And I've done this before many times, so I'm just going to move on now. Skip all of these. And this is the good stuff. This is the final set of expressions that we are left with, and this is what we use to make the actual driver in our simulation software. Okay, so here we are back in the simulation software, and I want to go back to the counter real quick. So previously we had determined that this is going to be A, B, C, D. But now we're going to be changing how we sort of name things. This is going to be W. This is going to be X. This is going to be Y. And this is going to be Z. So this is how we interpret things now. And we're going to be using these equations to design our driver. Now, another thing I want to point out is that obviously this device here has a driver built into it. So my goal is to, make a driver from scratch. Because in reality, what's inside here, these type of devices, is sort of a wide array of logic gates that is able to interpret binary number that's coming in here. Okay, so here we are in the software again, and we're looking at this display here. Now this display doesn't have a built-in driver, so we need to make our own in order to make this one function. And you'll also notice that it has the A, B, C, D, E, F, G uh, right here for each of the pins. So what we have to do is now look at each of these expressions and figure out how to wire up these outputs. So if you look here, you'll see that I already did it, but let's look at the first part of the circuit. So we're going to start by looking at the outputs of each of these, and then we know that this one corresponds to W, this is X, this one is Y, and then this one is Z. And so we're going to bring this one out. We're going to keep this one that has the driver built in, and then we're going to drop down sort of a bus that goes down, and then I have it labeled here W, X, Y, Z. And then we also need the inverted version of each of these. So we see here that the inverted version of these outputs is simply going to be this pin here on each of the flip-flops, which is this one and this one. So take a close look here. I'm outputting them here, right here. So these four is the inverted out versions of it. So then we have here W naught, X naught, Y naught, Z naught. So let's go ahead and start looking at the first one. So this one corresponds to A. So then we see that A is we start with this one here. So it's W naught, X naught, Y naught, and Z naught or Z. So we start here. We start. This is W naught, and then it's ANDed with this X naught, and then we have another logic gate, which is Y naught, and then we take Z from here. So that's where this comes from. And then that has to go into another logic gate here. And so this output here essentially corresponds to W naught, X naught, Y naught, Z. The next one we need is this one on the left, which is X, Y naught, Z naught. So then we come down here, take X here, take Y naught from here, and then we take Z naught directly from here, and then put it into this other AND gate. So then this AND gate, I have it actually labeled here. So this is actually X, Y naught, and Z naught. This is supposed to be a Z naught here. Let's fix it. Okay. So then we can pick a random one here, and we can, so let's pick this one here. This is going to be F, because as we go down here on the list, it's basically A, B, C, D, E, F, and G. So that, and obviously you can see that corresponds to these letters here. A, B, C, D, E, F, G. So let's go down. Let's pick a random one. Let's see. Let's pick this one. So this is A, B, C, D. So here, we're going to look at D now. We see that D actually reuses the one from A. So we see that we are reusing this one. And then here, we see we have X naught, Y naught, Z. So that comes from this expression here. So first we grab X naught, which is this one. We can see here. And then we grab y naught z. And y naught z is already has already been made. In fact, I had to label some here and then look at this carefully. Yeah, so if I'm looking at x naught, y naught, z, it's gonna be this one here. So you'll notice that here I'm grabbing x naught, and then y naught, z is this one. So I was lost for a good bit here, but yeah, here it is, and it makes sense. So I'm combining y naught, z, which is I grab it from here, and then I'm combining it with the x naught, and therefore I get x naught, y naught, z, and then that is placed into this OR gate where, and then if you look at the next part of the expression here, x, y naught, z naught, I already have that, so I'm reusing it up here. So I'm bringing it down and then I'm putting it into this OR gate. And then there's one last expression that I need to make for this one, for this logic gate to be good, to, to be correct with this expression. And then it's going to be this one here. So x and y, I already have that. So that is coming from, let's see, right here. This is x and y, and it's coming down here. And then this one is going to be z. So now I combine x and y and then z. So that gives me x, y, z for this AND gate. And then I put it in here, and then that finalizes the equation D and for these logic gates. And then obviously that goes into the display here. And yeah, so this is actually significantly simpler than the hexadecimal display. The hexadecimal display had much more logic to it, but this one works. And then I guess I can look at the one that follows because it's very simple, very straightforward. So now I want to look at this OR gate here. So this is simply the Z. So then I grab Z from here. Remember, this is W, X, Y, Z. So I'm grabbing Z. And then I'm adding it to X, Y naught. And I already have that. And I've used it 3 times already. So this is the 4th time I'm using it. So I'm gonna grab it from here. So let's see how many times it's been used. X, Y naught. So we have it used here. 1, 2. So this is used once, twice. And then it used, I guess this counts as a 4th time used also. So there it is right here. No, sorry, right here. So this is the output for E. Yeah, this is the output for E. And here we have X, Y naught. So that makes sense with this one here. So let's go ahead and run it now. See what we get. And remember, this is only the 0 to 9 driver. I mean, there's only one type of driver, and it's going to be this one. This is basically the decimal driver, which translates binary to something that we can read, which is decimal. So we see here that it goes to 9 and then back to 0. And then I left the original display here, the one that has the driver built in, just so we can verify that it works. Because both of them should have the same number, so we see that they both have the same number, and so they work. Okay, so this is the overview of the circuit, and I still have it running. So one of the things that I want to point out is that the digital clock has 6 displays. And so what that implies is that I would have to repeat, let me show you, I would have to repeat this set of logic gates 6 times. So that's a challenge in and of itself. And then not only that, I have to figure out how to wire them all together. So let's go back to the diagram that we have here. The drivers, we can consider them as done. Change to black. Change to black. So now we finished everything. We did the counter. We did the drivers. We did the counter that goes from 0 to 59. And then we did the counter that goes from 1 to 12. So now what we need to do is we need to find a way to combine all of this together and make them work with one another such that we get a 12-hour digital clock. Okay, so it is at this point that we can begin to show some appreciation for the ICs that we have available for us to use out there, because if I was to use this driver for each and every single display that we're using in our clock, it would make my computer really, really slow. Maybe I wouldn't be able to even work with it. So what I'm going to do here is to continue about the conversation about appreciation, is that there are ICs that have drivers built into them, and there are ICs that have counters built into them also. So if we go back to this here, we're not going to be using our design, but we're going to be using an IC that performs the same function that our design performed. So this is one of the things about design, is that it's good to make your own, but it's even better to use a better version. So the versions that we're going to be using are let me see here. So for the counter, these 4 counters here, we're going to be using the 4518 BD 10 volts. So this IC is basically a counter, and it is a resettable counter, meaning we can count up to any number we want, and then we can pause or reset in the counter, making it go back to 0. These 2 counters, on the other hand, is going to be a different type of IC. The IC that we're going to be using for this one is going to be the 4510 BD 10 volts. So this IC is a different one because this one is a presettable. We can preset it to a set, and then this is simply reset. So with this IC here on the left, this 4510B, we can reset it to any value we want. So we can have it count up to a certain value, and then we can, when we perform a reset function, we can say, listen, I want to reset it, but I don't want to start from 0. I want you to start from 5 or from 6. So you can go from 6 to 12 and then repeat 6 to 12, or you can go from, and anything you want. But what we need is 1 to 12, like we have here. So we're going to make this set of counters go from 1 to 12. And then for this one, we simply need reset functions. So let's So this one, these ICs will suffice. This 451AB, and that simply goes it's gonna be from 0 to 59. So that takes care of the counters that we're gonna use. So now let's talk about the drivers that we're gonna use. Well, the drivers that we're gonna use it's gonna be the built-in drivers that are built into the displays, because I don't want to have too many ICs in my simulation. So we're gonna be using the integrated drivers that are in the displays. Okay, so basically, even though we're not using our designs, it's important that we were able to basically design each and every single one of these aspects of the clock, despite, not using our original, the designs that we made. But nevertheless, you know, we are using the ICs to our advantage, and not only that, but we understand how these ICs work because we designed our own versions here. We designed our own counter, we designed our own driver. Our own counter that goes from 0 to 59, and then our own counter that goes from 1 to 12. So let us proceed to the actual digital clock finally. Okay, so this is what the digital clock now looks like. This is the full working digital clock, and in fact, this is an adjustable digital clock as well. So here we have the first counter. The drivers are within the displays, like I said, we're using the built-in one. And let's see, so these are simply counters. So we need to make sure that they reset when this number reaches 9. So if you look here, it's going to reach 9 here. It'll reach 9, and then these two outputs will be triggered high. So that'll cause the clock to go low, and then that'll trigger the this display to go off, because we want the seconds to work like this, right? Once the seconds reach 9 here, we want this one to go up by 1, and then the seconds need to reset once again, 9 to 0, so on and so forth. And then additionally, we want the minutes to be triggered off of the seconds. So let's see what we're grabbing here. So one of the things is that this has to go from 0 to 59. So we're going to be looking at the case when this is equal to 5, or rather 6. See here? We have this is the least significant, followed by the one that follows, and then the most significant here at the end. And then this is actually equivalent to 5. Oh, no, equivalent to 6, I'm sorry. So then at that instant, when it reaches 6, it triggers a clock. And not only that, it triggers a reset. See here? Triggers a reset. Okay, so now we look at the minutes. So this OR gate, I'll explain what this OR gate does later, but when the signal is sent here, it triggers the reset. So then this should go back to 0, and then at the same time it triggers this clock. So then this clock it gets triggered, so then it goes to the 1. So then this is how, we expect this to work, when this reaches 59, right after 59, this should be, triggered, the minutes, right? This, because these are our minutes. So the same idea follows for the minutes, because we want the minutes to go up to 59. So we take 9 on this side, place it into the clock of the following, and then we are looking at this output here, right here, and whenever it reaches 6, it triggers an output on this line here, and it'll trigger a reset, and it'll immediately reset this one to 0, and then alongside this one will go back to 0 as well, because it has to go from 9 to 0. And then if we keep following the line, it'll also trigger the hour. Now these ICs are for the hours. Now you'll notice that these ICs look a little bit different. This is because these ICs are, you can preset them to a certain value. These other ICs, you cannot preset them, meaning they have to go back to 0. Whenever you do reset them, it goes back to 0. So let's go back to these. So let's see. So we have the clock coming in from the previous, from the minutes. So that triggers the clock, triggers the counter. So it should count up. So, but we want this counter to stop at 12, or to, yeah, basically to stop at 12. So we will be monitoring, which one is this? Let's see. Okay, so then the way these outputs work is that the least significant bit is on the left side. So you'll notice that this corresponds to 1, and then this one here corresponds to 2. So when this is 1 0 0 0, and then this is 0 1 0 0, basically these signals get activated. And well, obviously this is a 1 that is equivalent to a 1, and then a 2 on this side. So then what happens is both of these are 1, and then we have an active high here, and that goes to the preset enable pin of our ICs. So what the preset enable does is it basically puts the the counter back into this position, and the position is this here: P1, P2, P3, P4. So you'll notice that I have the preset enable gets activated, and then I want this specific counter to be preset to 1. So this is why I have line right here. So this is what will allow the counter to go from 1 to 12. Okay? This will go from, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we'll have 12, we'll have 10, and then we'll have 11, and then 12. And then the preset enabled is activated, and then it goes back to 1 because of this line here. Okay, so now we can look at these OR gates. And so what is this business about the OR gates? So these OR gates actually allow us to have additional control over the clocks of the clocks of our counters. So let's say the clock is running. I can turn on one of these switches, and what that will do is it will basically manually send a signal to these lines, and then that'll make this OR gate activate, and then it'll introduce a clock signal into the counter, and then it'll increase it by 1. So this is how we can make this an adjustable timer. And then likewise with the hours, this switch will control this logic gate here, and then if we send the 1 into here, this OR gate will activate, and it'll introduce a clock into this timer, or this counter rather, and then I can adjust my hours. So if we look here, this logic gate is for the hours, and this logic gate is for the minutes. So okay, so enough talking. Let's go ahead and let's run the damn thing. Okay, so let's run. And here it is. So I have now, my original clock is set for 1 second. And here it's running. But one of the great things that I can do is I can adjust this clock to my actual time where I am located. So right now it is 1:48 in the morning. Ask me why. So I can actually choose to pause the clock, and I can control these switches by pressing the numbers on my keyboard, 1 through 4. So let's see. I can pause the clock when I press the 4. I can begin to adjust. Oh, it looks like I went past the number, so I can just go all the way around. 10, 11, 12, 1. So now, and it's also important to make sure that I put these back in the off position here. Alternatively, I can replace these with momentary switches, like toggle switches, but these should work fine for now. Now I can adjust the minutes. 21, 5, 6, 30. So it is 1:50 morning. There you go. And then I can even adjust the seconds. So let me adjust the seconds also. Seconds be quick because it's gonna reach the next. In fact, if I keep adjusting, it should change it to 51. But let's see what happens if I keep going here. 45. 9. There. Okay, so that's good. Now I want to run the clock. So this seems like it's working great. It is, if I bring up this website here, this website tells me the time exactly. Okay, so after readjusting it, you can see that the clock is about 1 second behind. It keeps time relatively well and working nicely. I like the green font, makes it look like a real clock. So I'm gonna let this running for a couple seconds to see how much it drifts. Because I do believe that multisim isn't perfect when it comes to these type of things. But hey, this looks pretty good. Looks like I'm ahead by 1 second exactly. Is to 55, you saw that? Okay, I'm gonna pause it here, and then I'm gonna let it go for 5 minutes to see if when it changes for the hour. That'll be interesting. Okay, so here we are once again. It is about 30 seconds until 2 a.m. So what we expect to see in the hour is the hour to be at 2, and then we expect the minutes to go to 0 once the seconds reach 59. So we should see 2:00 is what we should see, 2 a.m. And there it is. It is now 2 a.m. The hours switch to 2, the minutes switch to 2, and then the seconds are counting up once again. So this clock is working very effectively and reliably. Okay, so if you have any comments or questions, please leave them down below in the comment section. If you like this video, don't forget to give it a thumbs up. And if you want to see more of this in the future, don't forget to subscribe. But that is all for now. Thanks for watching, and I'll see you guys next time.